Let's take a look at this substitution idea. The idea is we want to replace a piece of your differential equation that has a linear combination of x and y and constant ax plus y, ax plus by plus c, and then do the substitution by taking the derivative and stuff. And so what we want to do is we want to find a common set of linear terms. If we take a look at this example here, the first one is the numerator is 1 minus x minus y, and then the denominator is x plus y. So if I were to choose what the u substitution should be, I would probably want to choose, what would you choose? Would you choose the whole numerator, or would you choose the denominator? So I would probably want to choose the denominator because there is an x plus y that's common to both of them. And in that case, you can just look at that x plus y as your value or your substitution, so then you can get rid of all the x's and all the y's, or at least all the y's. That's what we'll do. Let's start off doing this example by letting u equal to x plus y. And then remember that when we're replacing something with a substitution, just like the u substitution in Calc 2, we have to find the differential to replace any of the dx's, dy's that we have. So here we have a dy dx, so we probably want to just take the derivative with respect to x. I mean, we can do the differential technically, but if we just do the derivative with respect to x, that's probably fine. So du dx, the derivative of x with respect to x is 1. And the derivative of y with respect to x is dy dx. So du dx is equal to 1 plus dy dx, and that will be our substitution. Of course, we want to solve for dy dx so we can do the replacement, and then we can change everything else. So we have a dy dx is du dx minus 1. And then we have 1 minus u divided by u. That look okay? And then now if we just fiddle around, we'll see this thing. Yeah. Say it again. We're gonna pretend that x is our independent variable, and we'll treat it like that. So there's some cases where we did that, and there's some other cases where we actually wanted the dx by itself. And so you just have to remember what technique you're using. So in this particular substitution, we want to say du dx and then dy dx. And so dx dx is equal to 1, or if there's a constant there. All right, let's add 1 to both sides. U dx is equal to 1 minus u over u plus 1, and common denominators or whatever. 1 minus u over u plus u over u, and then you get 1 over u. So that seems to have come out pretty simple, nice and easy for us. Did I do that right? All right. So du dx is equal to 1 over u. It'll be a separable differential equation like they mentioned, and then you would just integrate. So our integral is going to be u squared over 2 is equal to x plus c, and then you can solve for u here, but remember that the whole thing is you let u equal to something in the beginning, right? So let me rewrite this as 1/2, and then u squared, and then u was equal to, what was it? X plus y. And then if you can, you could solve for y. In this case, and actually a lot of cases, these are the times where it'll probably be a little bit more difficult to solve for y. Remember, when you try solving for y, when there's a second power, you have to take the square root. When you take the square root, you're considering the plus and minus of things, and so you're going to lose some parts of your solution. And if you don't have an initial condition to determine what part of the solution you want or you need, then it'll be kind of difficult to solve for y. So I would call this this is a general solution, but it's also an implicit solution. And for most cases, because we do u and then we solve for u and then we're going to replace it back with x and y, unless the u that we get is actually a nice function, a linear function, then chances are you're going to leave it as an implicit solution. All right, questions? All right, let's try another one from this set. Let's try number 30. So here we have dy dx equals to 3x plus 2y in the numerator and 3x plus 2y plus 2 in the denominator. And then we have an initial condition. So after we solve for the general solution, we'll need to solve for the initial condition. And maybe we'll take a look at a graph of the solution. But for now, let's see what is our u going to be here? The top one again. And then du is going to be 3 plus 2 dy dx. Oops, this is du dx. So dy dx should be negative. What is it? Du dx minus 3, divide the whole thing by 2. Okay, so let's see if we can put it all together. This is going to be du dx minus 3 divided by 2 is equal to u, and then u plus 2. So let's do some algebra. Let's bring the 2 over to the other side, and then we'll add 3. Du dx is equal to 2u over u plus 2. This is the 2 being multiplied, and it will add 3, but we want to add with common denominators, so we're going to say u plus 2 over u plus 2. So there's 2u and 3u, 5u plus 6 divided by u plus 2. So that's what du dx is equal to. It's separable. We'll bring all the u's to one side. So I need to multiply by the reciprocal. U plus 2 over 5u plus 6 du dx is equal to, I'll just say du. Now we have to integrate that thing over there. We could do partial fractions. Um, uh, we could probably split it up. Yeah. Are you talking about where are we here? Yeah. And then I would have a minus 2 up on top. I suppose, is that, would it be easier? Let's see. That would be, because we're still going to add and divide by stuff. And so, if it is easier, it might just be a coincidence. I don't know if it'll necessarily be always like that. But we could try it, or somebody could try it and report. Let's go with this for now. It looks like we could do partial fractions, but you know, this is, can't really do partial fractions. So anybody know how to integrate this? It is a sum up on top, right? You can break it up. What? To simplify? How? Long division? Yeah, so we could do long division, simplify it. I was just thinking of splitting up the numerator. I mean, that would work too. That's kind of like usually what we say our first step is for partial fractions. But if we split this up, um, and then the first integral is some sort of u substitution that we need to kind of be careful about. And the second function, second term, is another substitution that's going to lead to natural log. So if we just do each of those integrals carefully, then we should be okay. So let's do it carefully. I mean, I would just put it into Wolfram alpha and be done with it, but we're doing integrals. So 5u plus 6 du, and then u, well, I can't do u substitution. Let's do v. v equals 5u plus 6. dv equals 5 du. And then you also need to replace this u. U is equal to 1/5 v minus 6. Bring the solve for the u up there so I can replace the u in the fraction. So let's see how this all plays out. This thing is going to be the integral of 1/5 v minus 6 divided by v, and then du is going to be dv over 5. Is that any easier? So 1 over 25 integral, right? 1 minus 6 over v dv. So this is 1 over 25 v minus 6 ln of v. And v was equal to 5u plus 6. 1 over 25 5u plus 6 minus 6 ln of 5u plus 6. Well, that was long. Is that right? I hope that's right. Yeah, does it look right? What? Well, this is just u substitution, isn't it? I mean, I gave this integral in my final exam for Calc 1. So, I mean, this kind of integral is covered in Calc 1. Yeah, it's just a u substitution. I think it's everything. Oh, yeah, the bracket here. All right, so we'll save the plus c for later. And now let's do the other integral here. This is the first integral, and this is our second integral. But this one's easier, right? Yeah, it's just a u. So there's a 2 out here, and then there's a u substitution, which will give you a 1/5. And then this is the ln of 5u plus 6. Right? So if any of these integrals are like kind of weird for you, then you should really look over it, practice it, do it again, from start to finish, because I want you need to be able to integrate in this class, right? Yeah. Yeah, absolute value. I'm kind of looking ahead, and our x is going to be, actually, we need to worry about that after we put everything back. So yeah, the absolute value is probably going to be important for us. Okay, so what do we have? We have these two things. So on the left-hand side, it'll be 1 over 25 integral of 5u plus 6 minus 6 ln 5u plus 6. And then we have a plus, that is a plus, right? 2 over 5 ln of 5u plus 6. We can combine these two terms here once we get the 1 over 25 in there. And then here's where we throw in the plus c. All right, so let's see if we can combine this. This is 6 over 25 negative 6 over 25 plus 2 over 5 minus 6 over 25 plus 2 over 5. What is that? 4 over 25? Negative, right? Negative? Positive. Positive 2 over 25. So 1 over 25, 5u plus 6, positive. What did we say? 4 over 25 ln 5u plus 6 plus c, oops, equals x plus c. All right, and now we need to replace with, what was it? 3x plus 2y, where the u is. Wow, this is a mess. Well, you would normally leave your answer like this, but we're not quite done yet because we have an initial condition, so we need to solve. All right. So this would be our general solution. And I'm looking at it, it's pretty hard to solve for y by itself. So I would leave it like that as a general solution answer. But then we have our y of -1 equals -1 initial condition. So we want to put -1 in for x and -1 in for y, and then see what we get. So we get 1 over 25, 5, 3 times -1 plus 2 times -1 plus 6 plus 4 over 25 ln of the same thing. 5 times 3 times -1 plus 2 times -1 plus 6 is equal to -1 plus c. And solve for c. This is -5, -25 plus 6, 19. So 1 over 25 times 19 plus 4, was it 19 or -19? Negative, yeah. And then 4 over 25 ln, so this is where the absolute value would be good, because if you didn't have the absolute value, then it would be a negative in the ln, which is not going to work. Is equal to -1 plus c. So c is equal to, there's more stuff here. So -19 plus 25 is 6. Positive 6 over 25 plus 4 over 25 ln of, I'll just say 19 positive. So that's what the constant is. Oh, yeah. That's what? This is one problem. So that's what c is equal to. So your final answer is 1 over 25, 5x, 5 times 3x plus 2y plus 6 plus 4 over 25 ln of 5, 3x plus 2y plus 6 is equal to x plus all this other stuff. 6/25 plus 4 over 25 ln of 19. No, this would be your particular solution now. This would be your solution after you found the C, and you found the C from your initial condition. So this is our general solution in the blue with a plus C, and this is your particular solution. Yeah. Yeah. Initial value problem, IVP, yeah. And then sometimes I say IC for initial condition. I was going to put IC here, but later on I'll just put IC. Because I have to write initial condition. Not like you can read my writing anyways. So, yeah, I mean, if you look at this, this is only half a page. Wait till we get to chapter 7, chapter 6 and 7, 8. Oof. Each problem would be like 2 pages long. Yeah. I wanted to graph this, but now I don't know if I want to graph it anymore. I suppose you can graph it. Sure, we got nothing else to do. Although there is like a party today, staff party. All right, so let's see if I can figure out how to graph this thing. 1 over 25, and then we have 5 times 3x plus 2y, and then a plus 6 on the outside. So I'm going to take this expression and copy it. All right, and plus 4 over 25 times the ln absolute value of that same thing is equal to, let's just put x, and then let's put plus c for now. And then I have to say what c is equal to. Actually, they're going to assume, this program is going to assume c is equal to 1. So this is how the graph would look like. And we want to make sure we include this point minus 1, 1 in the different c values that we get. So if we, I usually just like to mess around with this a little bit and guess at what c might be. C is equal to -3, and then c is equal to +3. So at some point over here, one of your families of the curves will be hitting this point, and it's probably between somewhere 0.75 to 0.66. So what we want to do is we want to add this constant. This constant here is supposed to be our constant that's going to make that hit the point. And so let's change the c into 6 over 25 plus 4 over 25 times the ln of 19. And there we hit the point. And I don't know if you tried putting this into your calculator, but it's, what is it? 0.7 what? 0.711, so it's between 0.66 and 0.75. And so as you're examining it, you can kind of see what your solutions might look like. Say it again? Can you check using the calculator? The calculator, unfortunately, doesn't graph implicit functions, and this is an implicit function. And so no. The 84s, 83 and 84s are really statistics calculators, and the 89s are more like the calculus calculators, and so they would have a better chance, and they might actually do slope fields. Or if you have the Inspire, I don't know what number it is, but one of those Inspire calculators, they might automatically have the slope fields. But in terms of actually programming it to graph, I don't know if I can. I don't know if it can be done. But Desmos would allow you to graph implicit graphs. So if you go to desmos.com and look it up, or just type in some equations and see. Yeah, probably. Or I might have a selection of graphs and then you choose which one the slope field should be. Oh, so so I mean, I don't know if I'm going to do this on the test, but one of the possibilities on the test is I give you a differential equation, and then you have to figure out what the slope field would look like. And then so you just have a choice of 4 slope fields, and you have to choose the slope field that it matches. And then you remember how we did slope fields in the beginning, right? So we just plotted a couple of points. So if you look at the graphs and look at, say, there's a slope. I see a slope on the point 1, 1 or something. So I'll plug 1, 1 into the equation, and I'll see if that slope is positive or negative, and that's going to give me a little bit of a hint. And then I'll try another number. If it's steeper or less steep, then I should be able to make my guess or my assessment that way. All right. So let's move on. Oof. Oh, we should have done a trig one. Oh well. Moving on. So um, people would try to solve for differential equations, and then there are some differential equations. Out of all the techniques that we've learned, there's still going to be a handful of differential equations that we won't be able to solve for. So in those cases, just like in integrals, what we decide to do is we decide to just try to approximate it or do it numerically. And so we're going to take a look at a numerical method called Euler's. Is it Euler's? Yeah. It's Euler's method that takes a look at this first order differential equation and looks at it as if it was a slope field. So you have to have, it has to be an IVP, it has to be an initial value problem. So it has to have a differential equation and an initial condition. And what you're going to do is that from that initial condition, you're going to kind of take a guess using the slope. Take a guess by using the slope, and then the bigger steps you take, the more error you're gonna come up with. So the smaller steps you take, the less error you're gonna deal with. This is the rundown. I think it might be better if we take a look at the graphical approach first, and then we can see if we can match our intuition for the graphical approach with the symbolic stuff that you see here. So let's do a problem first, and we'll scroll back up there. And I don't know if I remember how to graph slope field here. Have I done a slope field with this? Uh, all right, I want to waste time thinking, so I don't want to think. Let's do another slope field. Desmos has them. Oops, tendons. What was the function that we were working with? That was, oh, that's not, with the differential equation. This thing. Okay. All right. So 3x plus 2y, and then the same thing. slope grid, movable point. Can I manually change this? -1, -1. There we go. So I don't know if that was the best slope field that we can get. We could probably have done it a little bit finer. All right. So if you look at the graph, it kind of, if we follow this point, we'll see that there's going to be some issues right here because it's going to be vertical slope, and then when we keep following that graph, it'll no longer be a function anymore. So there's some issues about the implicitness of this thing. But if we can get up to here, maybe that's one of our goals, maybe. And so the idea is that from here, what we're going to do is we're going to look at the actual value of this slope. So we're at the point 1, 1, or -1, -1. And then the slope at that point is whatever value we get when we put -1, -1 into the original differential equation. So dy dx, what was it? It was 3x plus 2y, 3x plus 2y plus 2. So if we put -1, -1 in there, we're going to get a -5 in the numerator divided by -3. So it's positive, and that kind of matches with our graph. It's 5/3. It's bigger than 1, so it's a little bit steeper than just a regular diagonal. So we're going to go in this direction. And depending on how big your step is going to depend on how exact or how fine your graph is going to be. So if we take a little step, and usually little steps, a good little step is like 0.1. So if we take a little step and we follow this graph up to the little step, what's going to happen is that we're going to approach another point following that line. And then from that point, we're going to try to find the slope. So whatever this new point is, I don't know what it is, but I don't want to try to figure it out. But whatever that new point is, I'm going to put that back into the differential equation to get a new slope. And the new slope will tell me which direction to go again. And then I'll take another little step, and then I'll get another new point, etc. So I keep doing that to as many steps as I want to get to a certain number that I might want. So a lot of times these differential equations start off with an initial condition, and numerically I just want to find out the value at a particular point of the value of the function at another point away from the starting point. And so this is a numerical way of getting there. Ali? Along the linearization of this one, and then once I get a new point, I'm going to repeat the process. I'm going to get another new slope. And then I will take another little step and I'll stop at another point, and so I'll have another new point. So I'm going to keep building myself new points. Now, because this is a tangent, I'm only good if I'm close to the point. So if I take a step of 1, take a whole step of 1, then I'm all the way over here with my next point. And then it looks like my next point is going to go this way, or it's going to be this steep and then this steep. So if I take my steps too big, then I'm probably not going to get a good line or a good graph, especially if I want to get, a little bit farther away. So does that idea make sense graphically? So graphically, that's what we're saying. Symbolically, this is what is happening. So you have your original differential equation. This is your initial value problem. And then you create a line. This is really y equals mx plus b, except, written in a fancy way, right? So you have your m x minus x naught, and then here you had y minus y naught, but the y naught goes over to the other side. Or if you want to look at this, this is like Taylor's polynomial, except for lines only. If you do Taylor's polynomial and you stop at a line, this is what you have. If you go quadratic, then you have the second derivative divided by 2 and all that stuff. So here, this is just a linearization, so this is just the equation of the line. And your slope is the differential equation, right? Because dy dx is equal to whatever it is on the right-hand side. And now you're going to take a little step. So you're going to put in a value of x that's a small step from x naught. And so that distance here, x minus x naught, where this is the next point that you're going to go into, that step is h. The difference between your initial value to the next little value is going to be h. And so you put that value in, x minus x naught, and that becomes h. And then you're going to get a new y value. And then that new y value is going to be your new starting point. And then you're going to, from this y value, from this x1, y1, you're going to come up with another slope. You're going to take another little step, and then you're going to get x2, y2. Okay, so in the x-axis, you're just taking steps incrementally, the same steps. Until you decide that you need to stop somewhere. And these steps are all steps of h. That's your step size, they call it sometimes. And then as you take a step and you move along that tangent line, you're going to get a new y value. And then from there, you're going to recreate the whole problem again, take another little step to the right, and then you're going to get another y value. And so those y values, the set of y values is going to be y sub 0, y sub 1, y sub 2. And then in the end, you're going to get y sub n. Okay? And that's what we're shooting for. We're trying to find out what that last y value is. So, is there an example? So let's take a look at a simple example. I don't know, we want to do 3 or 4. Let's do number 3. So they want the steps to be h is equal to 0.01 and 0.005. So let's do a couple of examples here, or a couple of ways. Well, this is your initial value, your initial condition, right? And then this is where you want to get to. And so, so the question is, let's say you're doing a problem in your engineering field, and then you find this differential equation, and then you have the initial condition y of 0 is equal to 1, and then you want to know what happens at the solution when x is equal to positive 1. So here's where you want to start. You want to start with 0, and you want to take increments of 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, and then, so you want to take steps that lead you to 1, and then you want to know what happens in the y values. You want to know what happens up here to get to that point. Counter lines? I don't know. It could be. Yeah, it could be. Um, but I think this is more directed towards graphs that have information about the slopes. Those contours might not have information about slopes. All right, let's see how this is going to go. Um, how does it go again? Oh, equation of the line, blah blah blah. All right, so this is my x naught. This is my y naught. That's my starting points. I want my x. So when my h in this case is equal to zero point 0.1, that's going to be my step size. And my n, so this is h of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be x sub 10. So I want to see what happens at x sub 10. So I can have a list of points here already. I can put it on the left or on the right side. Let's put it here. X sub 0. Uh, yeah, it's tedious. X sub 0 is equal to 0. X sub 1 is equal to 0.1. X sub 2 is equal to 0.2, x sub 3, x sub 4, x sub 5, x sub 6, 7, 8, 9, x sub 10. And then I'm going to try to match it up with my y's. So these are the things that I'm going to look for. The first one is 1, y sub 1, y sub 2, y sub 3, y sub 4, y sub 10. So the x's are predetermined. I know what the x's are. All I have to do is I have to know my starting point, my end point, and my step size, and I know all the x's. The y's are the y's that I have to look for. So what are these values? And these values are usually, long, ugly decimal points. So I want to know what those values are. All right, let's get to it. So to get our first y sub 1, or to get our first y sub 1, we get y sub, let's call it L of x, is equal to y of 0 plus the m, what they call it, m sub 0? What do they call it? Y prime. So this is the graph that we're looking at, or this is the function that we're looking at, and we can call this h since this is going to be the same step the whole time. So when we go from the first one, 0 to the first step, and first step to the second step to the third step, it's all going to be 0.1. So we need to figure out what this is. So f of x is going to be 0, y is going to be 1. The slope is going to be whatever this function is, right? So what is the slope going to be? This is your first slope. It's going to be 1, right? Because it's just a y. There's no x's there. So I put y equals 1. And so I will have y sub 0 plus 1 times 0.1. And so this is going to give me my first y value that I'm looking for. What is this? 2.1? 1 plus, oh, wait, 1.1. 1.1. I was adding 2. All right, so now I'm going to come up with my new line. Maybe I'll call it L2, I don't know. X is going to be y sub 1, the new y sub 1 that I just found, plus the function evaluated at x sub 1, y sub 1. And then here I have x minus x1, which again is going to be the step size, h. I probably should stop putting x minus x1 there and just say this is h. And then now I need to put my x1 is 0.1, but there's no x's in here. My y1 is 1.1, so your slope m1 0.1 and 1.1 is equal to 1.1. So this is the function that I'm looking at. So y of 0 or y prime is your f of xy. And that's what I'm using to find my function. In this case, it's just y. It's a really simple example. I mean, we know the answer to this already, but it's good to do one of these numerical problems with a problem that you know the answer to, so you can check to make sure it's close. So we get 1.1 here, and then y1 again was 1.1. So we have 1.1 plus 1.1 times 0.1. Is that easy? 1 point. Is this 1.11? 1.21. Okay. So I'm already done with this. So you can use technology to figure this out. Um, the technology that I first like to use for this is Excel, because Excel can do something like this. This is simple enough. And in Excel, I can click and drag. I can click and drag things to get my values. So let's see, these are my x values and my y values. And then I probably want my f of x, y value. I don't know which one I want first. So anyways, I know that this is 0, 0.1, 0.2, right? And if I just click and drag, it'll do that for me. I think I do want these things switched. Maybe I don't want to switch. I don't know what I want. You know what you want? What? Yeah, I don't know if I want to delete it, but I guess we'll delete it. All right. So this is the number that I eventually want, right? So I need to figure out what this number is. This number is equal to y, right? That's just equal to y. Now, if I click and drag this, it's going to give me zeros because I don't have any values for this yet. But this is the next value that I want. So how did I get y1? I got y1 by looking at the previous y. We should look at this formula over here. I can get y1 by looking at the previous y. So this is equal to the previous y plus h, which is 0.1, times the slope, which is the previous slope. right? And then I think that's it. So if I press enter, that's the 1.1 that we got. And then the next one should be 1.2. And then there you go. So this is our solution. Well, kind of our solution. Um, do you remember the actual solution to this differential equation? Can you look at this differential equation and without doing Newton's method and then just doing whatever it is that we've done in the past, do you know what the solution is for this? E to the x, right? And then the constant that comes out, if you use the initial condition, y of 0 is equal to 1, you put 0 and you get 1, so that coefficient, it's actually a times e to the x, but when you solve for it, a is going to be equal to 1. So we know that this is your solution to this particular differential equation. Now let's compare our x values with the actual solution, e to the x. Okay, so what we want to do is we want to see what happens to e to the x. Well, we can go through the steps, but actually, let's not. We just want the final answer here. And e to the x is equal to e. Well, e, we want y of 1. So we want to put 1 into e to the x. And what happens when you put 1 into the e to the x function? You get e. What's e equal to? 2.718-ish. And so our approximation gave us 5.9, whatever, 5.93. So that's fairly close, isn't it? Yeah. Yeah.
Go back on the slide. See that formula? It says like y1 plus f of x comma y. So the part where it says f and then parentheses x comma y. So you don't do e to the 0.1. You just do 1.1.
No, because you don't know the e as your answer.
So you
right. That's the point, is that you don't know what the solution is, and you're trying to approximate what the solution is. Now, in this problem, we know the solution is, so we can check. But the real use for this is for the differential equations where you can't solve for. If you're interested in repeating this process where h is equal to 0.5, we can do the same thing, except our steps will be 0.5, right? So the idea there is that it'll take a little bit longer to get there, but we should be able to get it. Oops, cutting and pasting. So f of xy, and then these are your y values. And then this is always going to be y. So remember, when we started this off, it all started off with 0 until we figure out what y is equal to. So what was it again? This is y sub 0 plus the step size. This time the step size is 0.05, and then times, oops, I wasn't done yet, times the slope. Oops, that's the previous slope. And so if we take a look at the end of this, we see that we got 1.59 before, now we got 1.65. That brings us a little bit closer to I'm sorry, we had 2.59 before, and now we got 2.65. That brings us a little bit closer to our real answer. Okay. So here's the work for 0.01 in your graphing calculators. And just to remind you, for your notes, just to remind you here, we put equals, and then we put this y sub 0 plus the slope times the step size. And that's h. Whoa, what happened? Okay. Any questions? So when you guys do this, feel free to use technology. Actually, I think I should just force you to use technology. And since you guys are going to be like engineers, right? Or something, computer science people. Uh, then you should have some experience with Matlab. Too bad. So, all right. So the first worksheet we did as a group, this one you're going to do on your own. So already posted in your Canvas account, there's a worksheet here. And the worksheet is going to walk you through Euler's method using Matlab. And so all the commands are written here. All you have to do is copy this and paste it onto your Matlab program. And this starts off by defining your function. And then you start off with your initial conditions. Right? Instead of x's, we'll use t's. And then define your step size. And what you're going to do, and then figure out where you're going to stop. And what you're going to do is you're going to make essentially a vector, or let's just call it a list of numbers. You're going to make a list of numbers for your x values, or in this case, we'll call it your t values. And then you're going to initially start off with a list of y values that are all ones. And then what you're going to do from there is you're going to do some sort of for loop, iterative for loop process that essentially what we did in Excel when we did click and drag, right? And not only that, we didn't get to do this in Excel. You can't do this in Excel if you want, but you're going to actually plot it. So you're going to plot your graph, okay? And then you're going to do another set of numbers using a smaller step size. Go through the same process, and then now you're going to plot two of them. And if you look at this, you should be able to see what the difference is between the two plots. The O and the R. R is red, the O is a symbol. You're going to have a bunch of O's in your graph. Okay? And then, not exactly the real solution, but Matlab and many other people have a different algorithm for getting a more precise solution. And in Matlab, it's called ODE 45. And so that will give you a more refined solution And what you're going to do is you're going to compare all three of them. The one where you take a small steps, a reasonably small step size, the second one where you take a smaller step size, and then the one that would presumably give you a more exact solution to your differential equation. And then you're going to compare all three of them. Okay? So I want you to do this exercise for 2 different problems. And I want you to do this in Matlab, and then I want you to copy all your commands and your outputs, and then copy the plots, because the plot's going to pop up in a different window. So I want you to take a snapshot of those plots and then paste it on your document, and then I want you to submit that online. Question? You cannot download Matlab for free, but there are 2 free programs that are available. One is called FreeMat, and then the other one is called Octave. So they're on the top of this page. You can go to their website to see how you can download it. I think Octave works better if you have a Mac, and then they both work fine for PCs. Question? All right, this is due a week from today. Oh, and on Tuesday we're going to have a quiz. So by now we finished chapter 2, and you know a bunch of different techniques. What I'm going to quiz you on is I'm going to show you a differential equation, and you have to think what kind of differential equation that is so you can try to solve for it. But you're not actually going to solve for it. Yeah, so what method you're going to use. All right, so try to write down all the different methods that you learned, and then be ready to look at a differential equation and decide which method to use.